For countless generations, Mars has not only been a blazing red planet in the night sky, it has also been a symbol of humanity's aspiration to conquer the universe. The more we study it, the more we realize that this planet and Earth share astonishing similarities, enough to spark the question, could humanity one day turn this place into a second home? In today's video, we will explore the bold vision of a colony on Mars, along with the opportunities and challenges awaiting humankind. If you are also curious about the journey toward the future, make sure to subscribe, follow, and stay until the end of the video, because what you are about to hear may change the way you look at life beyond Earth. From the moment humans first began observing Mars with rudimentary telescopes in the early 19th century, the red planet has ignited powerful imagination. Could there be life, a civilization that once existed there? Although today we know that many of those early notions were based on limited understanding, uh, what is remarkable is that the fascination has never faded. On the contrary, thanks to modern technology, the hope of finding traces of life, even if only in the form of microorganisms, is increasingly reinforced. This very curiosity has driven a series of space exploration missions, from Viking in the 1970s to the familiar names of Curiosity, Opportunity, and most recently Perseverance. All of those spacecraft carried not only scientific instruments, but also humanity's dream of one day setting foot and living permanently on the red planet. What makes Mars an ideal candidate for settlement lies not only in its relatively close distance compared to other reachable planets, but also in many features that make it more familiar to Earth than any other world. Today, space agencies and even private organizations, such as the Mars Society or commercial space companies, have set forth a clear vision to turn Mars into a place humans can call home. But to transform the dream into reality, we must face a series of unprecedented challenges in human history. First, let's imagine the journey. Even with optimized launch technology, a trip from Earth to Mars still takes about 3 months. That may sound shorter than a transoceanic voyage by sailing ship hundreds of years ago, but the environment astronauts must endure is far harsher. During that entire time, they will no longer have Earth's magnetic field for protection, which means their bodies will be continuously exposed to cosmic radiation and solar wind. These radiations not only increase the risk of cancer, but can even cause nerve damage, leading to symptoms similar to Alzheimer's while still en route. This is a danger that cannot be underestimated, which is why scientists have proposed several creative solutions. One is to surround the spacecraft's living quarters with water, a natural material rich in hydrogen that can effectively absorb radiation. Another, bolder idea is to generate an artificial magnetic field to shield the ship, though this technology currently remains beyond our capabilities. Overcoming radiation is only one part of the equation. Communication also poses a major challenge. If you imagine making a call to loved ones from Mars, it would take 3 to 22 minutes for the signal to reach Earth, and just as long for the reply to come back. An ordinary conversation could become nearly impossible. This means that astronauts and settlers must learn to solve problems on their own, as instant support from Earth simply won't be available. In emergencies, waiting for instructions from Earth could mean losing the chance to survive. Now, suppose all the challenges of the journey are solved. The next question is, where will humans settle on Mars? Some potential areas have been identified, such as the polar regions, rich in water ice, or large craters like Korolev, which contain significant ice beneath sediment layers. There is even evidence suggesting the existence of underground aquifers deep below the surface, which could open the possibility of settling in the warmer equatorial regions. The advantage of choosing near equatorial areas is that solar energy will be much more abundant and efficient, making it easier to operate solar panels. At the same time, lower altitude regions also provide slightly denser atmosphere, which helps spacecraft land more safely. Another equally attractive option is ancient lava tubes. These are massive tunnels formed when flowing lava left hollow cavities inside. On Earth, we have discovered many such caves, and on Mars, there are lava tubes large enough to build entire settlements inside. The advantage of living in caves or lava tubes is that the natural rock above acts as a shield against solar radiation and small meteorite impacts. This significantly reduces the need to construct thick protective structures on the surface. But no matter the chosen location, one thing is certain: building habitats cannot rely entirely on human labor. In cumbersome spacesuits, manual work for hours is unfeasible. This is where robots and artificial intelligence play a crucial role. One idea many research groups are supporting is the use of 3D printing technology to create structures from Martian soil and rock, regolith. Autonomous robots would mine, process, and combine it with water ice to produce a concrete-like material, then print it layer by layer, gradually building radiation-resistant houses. Although the technology is not yet perfected, if successful, it would greatly reduce the mass of materials needing to be transported from Earth while enabling sustainable infrastructure directly on the red planet. Of course, construction is only the first step. These habitats must also generate breathable air, stable temperature, and appropriate pressure. A feasible solution is to utilize the abundant carbon dioxide in Mars's atmosphere to produce oxygen through electrolysis. This method not only provides oxygen for life, but also generates hydrogen, a valuable fuel source to refuel return flights to Earth. Combined with air recycling systems similar to those on the International Space Station, humans could fully maintain a closed atmospheric cycle for long durations. Thus, the journey to conquer Mars is not just a story of rockets leaving the launch pad. It is the combination of science, engineering, perseverance, and humanity's boundless imagination. Each solution, from radiation shielding, choosing settlement sites, to 3D printing construction materials, represents a new step forward for humankind. Although the road ahead remains full of daunting challenges, every preparation today is laying the foundation for a future where Mars is no longer only the destination of robotic explorers, but the home of the first pioneers. One of the greatest barriers to building a colony on Mars is energy. Every activity, from recycling air, producing water, maintaining temperature, to operating scientific equipment and communication systems, requires a stable power supply. Without electricity, the dream of survival on the red planet would quickly collapse. That is why engineers equipped the Perseverance rover with the MOXIE module, a small experimental device with enormous significance. MOXIE was designed to demonstrate the ability to produce oxygen from carbon dioxide in the Martian atmosphere, a breakthrough that helps transform the harsh environment into resources for humans. However, for MOXIE or any other system to operate continuously, we must solve the core question: where will the energy come from? The most viable energy source today is still sunlight. Solar panels have proven their efficiency on Earth and have also enabled many Mars missions to succeed. However, there are two major problems. First, Mars is farther from the sun, so the energy harvested is only about 40% of what the same panels would generate on Earth. Second, even if reduced efficiency is not a fatal obstacle, the massive dust storms on Mars remain a potential threat. These storms can last for weeks, even months, covering the sky to the point where light can hardly penetrate. The story of the Opportunity rover, which died after a global dust storm, is clear evidence of the fragility of relying entirely on solar power. Therefore, another option frequently mentioned is nuclear energy. A compact, safe, and durable nuclear reactor could provide stable electricity year-round, regardless of day, night, or dust storms. This is also the way spacecraft such as Curiosity and Perseverance have operated for many years. The problem is that mobile nuclear reactor technology for large colonies is not yet fully ready, but many projects are underway, such as NASA's Kilopower system, showing that this prospect is entirely within reach. In the near future, the optimal solution will likely be an intelligent combination of solar power, nuclear reactors, and backup battery storage. In this way, Martian settlers could both harness clean energy and ensure continuity in any emergency. If energy is the blood, then water is the breath of a colony. Without water, life cannot be sustained, nor can oxygen, food, or fuel be produced. Recent studies show that Mars is not as completely arid as we once thought. Beneath frozen soil, at the poles, and even in some craters, there are massive blocks of water ice. Extracting this ice, then filtering and sterilizing it, could provide several liters of clean water per day for each settler, the minimum needed to survive. But for a long-term colony, relying entirely on natural extraction would be risky. The reasonable solution is to combine ice mining with closed-loop water recycling technology. On the International Space Station ISS, more than 90% of water is recycled from astronauts' breath, sweat, and even urine. A similar or even more advanced system would form the backbone of sustainability on Mars. Thanks to recycling, the initially extracted water could be reused multiple times, significantly reducing the need for transport from Earth. Coupled with the ability to electrolyze water to separate oxygen and hydrogen, every drop of water on Mars would not only serve life, but also contribute to producing fuel for return flights or further exploration. Yet, water and oxygen alone are not enough. A true colony requires a stable food source. No one can bring enough food for an entire community for decades. The solution is to build closed-loop agricultural systems directly on Mars. This idea may sound futuristic, but in fact, space greenhouse models have already been tested in many laboratories on Earth. Some experiments in closed environments have shown that green vegetables can grow well under artificial LED light, providing fresh nutrition for the crew. On Mars, greenhouses will need to be specially designed to resist radiation and maintain stable pressure. Some scientists propose building greenhouses under soil layers or inside lava tubes, using natural rock as shielding. In addition, the chosen plants must be fast-growing, nutrient-rich, and efficient in regenerating oxygen. Potatoes, barley, kale, lettuce, all are potential candidates. More importantly, farming would not only provide food, but also bring tremendous psychological benefits. The image of an astronaut caring for green plants amid the red desert could become a symbol of human hope and vitality in space. Alongside crops, microbial cultivation or lab-grown meat technology could also play an important role. Microalgae, for instance, can produce oxygen, absorb carbon dioxide, and provide abundant protein. Meanwhile, lab-grown meat could help Martian settlers maintain a balanced diet without transporting livestock across hundreds of millions of kilometers. When combined, the overall picture of life on Mars gradually becomes clearer. A nuclear reactor supplies stable power, supplemented by solar panels when conditions allow. Recycling systems and ice extraction ensure a sustainable source of clean water. Greenhouses, microorganisms, and cultivation technologies provide abundant food while maintaining the atmospheric cycle. All work in harmony to build a mini biosphere in the cold desert. The important thing is that every technological advance serves not only Mars, but also has practical value for Earth. Innovations in energy storage, water recycling, closed-loop agriculture can all be applied immediately in resource-scarce regions on our blue planet. In other words, the journey to prepare for a Martian colony is not only a distant adventure, but also a motivation for us to improve the quality of life here at home. One of the most important pillars of any colony is the ability to sustain itself. On Earth, we have millions of hectares of arable land, abundant water, and a rich ecosystem to rely on. But on Mars, everything starts almost from zero. Therefore, the question of how to produce food becomes a crucial issue that scientists, engineers, and bioarchitects must solve. The first idea, seemingly obvious, is to take advantage of the surface soil, also known as regolith. On the red planet, regolith covers everywhere and could become the foundation for crops. However, the challenge is that this soil is nothing like agricultural soil on Earth. It contains many chemical compounds, particularly perchlorates, substances extremely toxic if humans absorb too much. Therefore, before sowing seeds, the soil must be washed with water to remove most of the toxins. Even after this step, regolith is still not fertile enough. It needs to be supplemented with mineral fertilizers and mixed with organic matter to create a loose structure that can retain water and nutrients, the ideal conditions for plants to grow. Laboratory simulations on Earth have proven that, when properly treated, regolith can support crop growth quite well. This shows that the prospect of agriculture on Mars is not far-fetched at all. However, relying only on soil still has limitations. Traditional farming requires large areas, significant water resources, and continuous soil improvement cycles. That is why researchers have also proposed a parallel solution: hydroponics and aquaponics. Hydroponics is the method of growing plants directly in nutrient-rich water without the need for soil. When combined with fish farming systems, we get aquaponics, a closed-loop cycle in which fish release nitrates, Bacteria convert nitrates into nutrients, and plants absorb them to grow. In return, plants filter the water for the fish, creating a sustainable cycle. In potential aquaponic systems on Mars, snakehead fish or other hardy species are considered ideal choices. They not only help maintain the nutrient cycle, but can also become a source of protein for colony residents. This is a dual benefit. The system produces both vegetables and edible fish. In addition, human organic waste, something often regarded as trash on Earth, can also be recycled into fertilizer. In a closed environment, no resource can be wasted. Another equally important factor is light. On Mars, sunlight is weaker and often obscured by dust. Therefore, cultivation greenhouses will need to combine natural light with artificial LED lighting systems. Modern agricultural LED technology allows customization of the light spectrum best suited for each plant, accelerating photosynthesis and shortening growth cycles. This means Martian settlers could harvest vegetables multiple times a year, that no matter how harsh the outside environment. Beyond meeting nutritional needs, agriculture also provides an invaluable psychological benefit. Imagine after hours of working in a stressful environment, astronauts stepping into a lush green garden, breathing in the scent of fresh leaves, watching life grow day by day. In the isolation of a distant world, that greenery would become a symbol of hope and a spiritual connection to Earth. That is why many experts consider planting not just a food necessity, but also a mental medicine for pioneers. Alongside growing vegetables and raising fish, another promising direction is microorganisms and algae. Microalgae have powerful photosynthetic capabilities, producing oxygen, absorbing carbon dioxide, and serving as protein-rich supplements. Some types of algae are even harvested to produce biofuel, providing renewable energy for small devices. Meanwhile, yeast and bacteria can turn organic waste into new nutrients, acting as recycling workers in the closed ecosystem. Thanks to this, the biological cycle of a colony will become increasingly closer to perfection. Once these solutions are combined, treated regolith soil, hydroponics, aquaponics, microorganisms, we can create a hybrid agriculture that is both flexible and sustainable. If one system encounters failure, others will ensure continuous supply. This very diversity will be the key to maintaining long-term stability. Notably, many technologies developed for Mars will also bring practical benefits to Earth. Water recycling systems, energy-efficient LED greenhouses, or closed-loop agriculture can all be applied in resource-scarce regions or densely populated cities. In other words, the race to conquer Mars unintentionally becomes a driving force for us to improve food security and protect the environment here at home. Finally, looking further ahead, building a sustainable agricultural ecosystem on Mars carries symbolic meaning. It affirms that humanity is not merely a species of travelers searching for new shelter, but also creators of life in a completely alien world. Every vegetable sprouting from regolith, every fish swimming in a tank, or every recycled drop of water is proof of humanity's boundless adaptability and creativity. And it is precisely those green gardens that will form the foundation for future generations to one day call Mars home. If energy, water, and food are the material foundations for a colony to exist, then human physical and mental health is the thread that determines the sustainability of the entire community. In a harsh environment like Mars, maintaining this balance is anything but simple. Because even if technology solves all basic needs, the human psyche can still become a fatal weakness. Imagine a typical day for a Martian settler. In the morning, they wake up in a small, enclosed room, surrounded by protective layers of metal and glass. Every sound is filtered through an artificial ventilation system. The scarce sunlight only reaches them through thick dust filters. They meet the same group of people, share the same portions of food, and repeat the same assigned tasks. Over time, this monotony can become a tremendous psychological burden. Experience from the International Space Station, ISS, or Antarctic bases shows that even in environments with direct communication to Earth, people still face isolation and prolonged stress. On Mars, this challenge multiplies due to the vast distance. Sending a message to Earth can take from 4 to 24 minutes, and returning is impossible in the short term. This means an almost absolute sense of being trapped with no immediate escape. That is why space psychologists have repeatedly emphasized only individuals capable of withstanding extreme pressure, possessing iron discipline, and extraordinary patience can survive long term. They must learn to coexist within a small group, handle conflicts tactfully, and maintain motivation even when their living environment offers no change. A small personal conflict, if left unchecked, can escalate into a crisis, affecting the entire community. Beyond psychological issues, Mars's low gravity, only 38% of Earth's, poses a major challenge to the human body. Research from astronauts living in microgravity environments has revealed long-term effects such as muscle and bone mass loss, vision degeneration, fluid circulation disorders, weakened immune function, and even changes in DNA structure. The famous case of the Kelly twins, one living long-term on the ISS and the other remaining on Earth, proved that microgravity can cause significant biological changes, some of which may be long-lasting or even permanent. On Mars, while gravity still exists, its much lower level than Earth's can still lead to similar consequences. To counteract this, Martian settlers will have to follow strict exercise regimens, using specialized fitness equipment to maintain muscle strength and bone density. A significant portion of each day may have to be devoted to exercise, much like astronauts on the ISS today spend at least 2.5 hours daily on it. In addition, cosmic radiation is a constant danger. Earth is protected by a magnetic field and a thick atmosphere, but Mars is not. This exposes people on its surface to much higher levels of radiation, increasing cancer risks and cellular damage. Settlements will require thick shielding made of regolith or specialized materials and may even need to be built underground to minimize exposure. Yet, even then, radiation remains a long-term concern. Another factor not to be overlooked is monotony in diet. Even if closed-loop agriculture can provide vegetables, fruits, and fish, the menu will certainly be far more limited than on Earth. Eating the same foods repeatedly for years can cause boredom and even micronutrient deficiencies if not carefully managed. To address this, researchers propose developing 3D printed food, using protein powder, starch, oils, and flavorings to create more diverse meals. This could become an effective tool for maintaining morale and motivation among Martian settlers. However, perhaps the greatest challenge is the yearning for connection. On Earth, we are accustomed to cultural and social diversity and broad relationships. But on Mars, a small community of only a few dozen or 100 people will have to sustain a closed culture. Every resident is not just an individual, but part of a fragile social ecosystem. Creating cultural activities, such as art, music, and group games, will be vital to dispelling boredom and maintaining cohesion. Through all of this, we can see that settling Mars is not only a technological challenge, but also the ultimate test of humanity's adaptability. Mental strength, collective discipline, and the ability to turn adversity into opportunity will determine success or failure. If successful, it will be the clearest proof that humanity is not merely a species dependent on Earth, but one capable of reaching out and creating life on any planet. Whenever the idea of humans settling on Mars is mentioned, the whole world seems to light up with a special excitement. Many believe it is an inevitable prospect, as humanity cannot depend on Earth forever. However, to turn this dream into reality, we need more than technological advancements. It also requires preparation in ethics, society, and even the mindset of humanity itself. Over the past few decades, technological progress has given us confidence that one day, colonies on Mars will no longer be just science fiction. We now have hybrid energy systems, 3D printing robots capable of building habitats from regolith, and bold experiments in closed-loop agriculture. Devices like the MOXIE module on the Perseverance rover have demonstrated that humans can produce oxygen directly from the Martian atmosphere. This is a turning point. If oxygen can be generated locally, the burden of transport from Earth will be significantly reduced. However, technology not only provides solutions but also raises difficult questions. One of these is the idea of genetic modification for astronauts. NASA and several research institutes have proposed designing humans to adapt better to harsh environments, minimizing radiation damage, resisting bone loss, even improving metabolism. In theory, today's gene editing technologies are capable of making some of these changes. But the question remains, is humanity ready to accept redesigning itself to conquer other planets? This is not only a scientific issue, but also an ethical and philosophical challenge. On another front, Human eagerness itself brings powerful motivation. Despite enormous risks and costs, tens of thousands of people around the world have volunteered for future Mars settlement programs. These individuals do not only see difficulties, but also recognize the great meaning, becoming pioneers of an interplanetary civilization. This is clear proof of the desire to transcend personal limits, willing to sacrifice comfort to open a new chapter for humanity. However, building a colony is not simply about sending humans there and keeping them alive. It also requires designing an entire social ecosystem. Questions that seem very mundane, such as who will be the leader? What legal system will apply? How will the economy operate? Suddenly become crucial. Even a colony of a few hundred people can generate conflicts. Without a clear governance structure, chaos could arise even if basic issues like food and energy are secured. That is why many experts suggest that early Martian colonies should operate more like extended research stations rather than independent cities. Every member must follow strict discipline, similar to submarine crews or scientists in Antarctica. Only when the population grows will cultural and economic diversity emerge, and from there, a new society will truly appear. And that is also when humanity must confront questions about Martian self-determination. Will they remain under Earth's control or gradually become a self-governing community? From a technological standpoint, this vision could arrive sooner than we think. In the coming decades, if compact, safe nuclear reactors are deployed, if extraterrestrial 3D printing technology is perfected, and if closed-loop systems run reliably, then a small-scale colony could take shape. But technology is only half the story. The other half is humanity's willingness to accept risks and make sacrifices. There is a reality we must acknowledge. The first settlers will not live in the dome paradise depicted in movies. They will face strange illnesses, resource shortages, prolonged isolation, and even high risk of death. Mars will never welcome us as honored guests. It will only allow those strong and determined enough to remain. And that is precisely what turns pioneers into symbols. Not because they enjoy comfort, but because they dare to endure hardship to pave the way for future generations. Looking back at history, every expansion of humanity, from oceanic voyages to the conquest of space, began with the daring of a small group. Settling Mars, in essence, is no different. But this time, the scale of the challenge surpasses anything we have ever known. It is not just a longer journey, but the task of turning a dead planet into a place with life. And if successful, we will not only have a new home, but also prove that humans are truly a species capable of surviving and thriving in any environment. In other words, a Martian colony will not only be a scientific project, it is a test of humanity's adaptability, creativity, and resilience. It is the first step in making the dream of becoming an interplanetary species a reality. And most importantly, it reminds us that the essence of humanity is never to stop. We always yearn to reach new horizons, even if it means risking our own safety.